I'd like to discuss the concept of stationarity, time series stationarity. This is an important concept in signal processing and is often very relevant for discussions in neural time series data analysis because the brain is a highly non-stationary system. So first, let's come up with a definition for stationarity. This will be a little bit of a sort of gooey semantic definition. But stationarity refers to whether the statistical characteristics of a signal of a time series are similar over time. So these statistical characteristics can include things like the mean of the signal or the variance of the signal, so the fluctuations in the signal, the frequency characteristics, or if you have a multivariate time series, we can also speak of covariance stationarity. And these are not the only statistical characteristics. There are also higher order characteristics like autocovariance, which is related to frequency, and skewness and kurtosis and these kinds of things. So you can already see that this definition of stationarity is going to be a little bit problematic because this signal can have or can exhibit mean stationarity but not variance stationarity, or a signal can be frequency non-stationarity but have a constant mean over time. And so there are multiple manifestations of stationarity. Furthermore, exactly what similar means over time and how to define and quantify similarity, how to identify a threshold above which you would call something a violation of stationarity is also a bit difficult, and people have tackled this issue particularly in the field of economics. But this is sort of in general what stationarity means, so let's take a look at some examples. Here we see two time series. One is has stationarity, and the other one has non-stationarities. And it's pretty clear that in this signal, the mean, so if you squint your eyes a little bit and kind of low pass filter the signal, the mean doesn't really change. The variance doesn't really change. So the size of the fluctuations are not really changing much from the beginning to the end of the signal. Here in this example, obviously the mean changes a lot or noticeably over time. And the variance, it's tough to say, but if you imagine removing this trend from the data, the fluctuations might be fairly similar in the time series in the beginning and at the end. So there might be variance stationarity in this signal. Here we have two other signals, data X and data Y. Clearly this has mean non-stationarities and this is mean stationary. Here I've plotted the running average of the means over time. So you can see that the mean does indeed increase here and not here. Here we have two other examples of variance stationarity, or I should say variance non-stationarity. Here you can see that the variance is increasing linearly over time. Here the variance increases and then it decreases over time. And a final example, here we have covariance non-stationarity. So there are three time series that are kind of plotted on top of each other here. And you can see that the mean and the variance are within each individual time series are stationary over time. But if you look at the pattern of covariance amongst these three variables, that actually changes over time. So this is an illustration of covariance non-stationarities. So why are we discussing these non-stationarities and stationarity? Now you know how the discrete time Fourier transform works. It works by computing the dot products between the EEG data, the neural time series data, and pure sine waves of different frequencies. So the EEG data, or whatever neural time series data you have, are definitely going to exhibit non-stationarities. The brain is a very strongly non-stationary device, and it is really no understatement to say that most of neuroscience data analyses are focused on identifying the non-stationarities in the brain. These are the interesting things when some dynamics in the brain change as a result of various cognitive or whatever processes. Okay, but in the Fourier transform, these sine waves that we use are always perfectly stationary. The sine waves don't change in frequency over time. They don't change in amplitude over time. And in fact, one of the assumptions underlying a Fourier transform is that the data are also stationary over time. And of course, this is not the case for brain data. So what I'd like to do now for the rest of this lecture is show you some examples of non-stationary time series in MATLAB, and we can see what the result is, what the implications of non-stationarities are for interpreting the results of a Fourier transform. Okay. So here we are going to create a few very simple signals. These will be 10 seconds long, simulated at a sampling rate of 1 kilohertz. And what you can see is that these are both sine waves with a frequency of, 3 hertz. And these two signals just change or they're different only in their amplitude. So either the amplitude linearly increases or it just stays the same. Okay, so let's start by plotting one of these time series. This is not a very interesting signal, it's just a pure sine wave. And now we can look at the second signal, and you can see that's a sine wave of exactly the same frequency, and this second signal exhibits frequency stationarity, but the amplitude increases over time. So let's see what the implication of that is for the result of the Fourier transform. You can see that both of these signals have a peak at 3 hertz, so that's good, that's the right frequency. But the amplitude non-stationary signal doesn't sort of go down very close to 0 right away. It has a more gentle slide down to 0. And in fact, even all the way down at 1 hertz, it's not really quite at 0 yet. This may seem a bit odd because in fact, we don't have any frequency components other than 3. There is no 2.5 hertz component that we specifically simulated in this data set. However, these non-stationarities in the data, in this case the amplitude non-stationarities, basically require that we have additional contributions of additional frequencies in order to perfectly represent this time series. So already you can see that having non-stationarities in the data make the result of the Fourier transform a little bit more difficult to interpret, a little bit less straightforward to interpret. That said, the Fourier transform is still a perfect reconstruction of, or perfect representation of the entire time series. And I don't show this in this code, but you can do this yourself by computing the inverse Fourier transform of the non-stationary time series, and you will see that you can perfectly, without any errors, reconstruct this blue non-stationary time series. So the Fourier transform is still accurate. It is still 100% correct. But the results of the Fourier transform are a little bit more difficult to interpret. Okay, let's take a look at another example. Here we are going to create a signal where the frequency characteristics change over time. This will be a very simple example called a chirp, where the frequency of the signal increases over time. So let's first plot this chirp. Here you can see the sine waves are starting out a little bit slower, and then over time they get faster and faster, and here they're much faster. And we can compare that with a pure sine wave, which is in red, but it's impossible to see. But anyway, so here, now this is quite striking, the result of the Fourier transform. For the red time series, this was the stationary sine wave. That looks exactly like what you would expect. We have a peak at 4 hertz, and it's extremely close to 0 everywhere else. Now for the frequency non-stationary signal, we defined this signal to change in frequency from 2 hertz to 10 hertz. And what you can see is that the Fourier transform shows a kind of broad frequency spectrum rising. Well, I guess the sort of edge is around 2.8 maybe hertz, up to, somewhere a bit under 10 hertz. So this is, on the one hand, not very surprising because that's how we define the signal, to range in frequencies from 2 hertz to 10 hertz. But it is quite striking to see what the effect of having non-stationarities in your data is for the result of a Fourier transform. It's also interesting thinking about the difference between the Fourier transform for an amplitude, when there's amplitude non-stationarity but frequency stationarity, where we get a sharp peak, versus amplitude stationarity with frequency non-stationarities, and here we get more of a broad plateau shape without any clear peaks. And again, this Fourier transform is still completely accurate. It's a perfect representation of the blue signal here, this sine wave, but it's just a little bit harder to interpret the signal based on the Fourier transform. Okay, so in this third illustration, we have amplitude stationary sine waves that just have sharp transitions. So it goes suddenly from 10 hertz to 2 hertz to 5 hertz to 8 hertz. And now, here you can also see that it looks a little bit similar to the amplitude non-stationarity example, in that there are sharp peaks, but and broad decays. And if you didn't see this time series or the time domain signal, and you just saw the frequency domain signal, you might actually think that this was just a noisy signal. But in fact, here you can see that there is no noise in this signal whatsoever. It's just that it takes extra frequency components to be able to capture these sharp transitions in the signal characteristics. So again, at the risk of being a bit repetitive here, this Fourier transform is a perfect reconstruction or perfect representation of the time series data, but the results of the Fourier transform are a little bit more difficult to interpret because of the non-stationarities. The final example that I want to show is of a sharp edge. So here the time domain signal is just zeros, and then at some point it bounces up to 1. And now you can see the Fourier transform of this sharp edge is quite ugly. And this is something that we would call an edge artifact. And edge artifacts are present in EEG data, particularly for task-related data, when you need to cut the continuous data up into epochs, which is almost always the case. So edge artifacts will rear their ugly head over and over again. Fortunately, edge artifacts are fairly easy to detect, as you can see here, and they're also relatively easy to avoid, or that is to say, it's relatively easy to avoid having edge artifacts negatively influence your data. Nonetheless, here you can see I have this additional component of the signal here commented out, so we can look at that. This is just to show you that that despite these non-stationarities, if you add a stationary component to the signal here, we are just adding a 6 hertz sine wave, that component still comes out of the data with the correct amplitude. So here you can see the amplitude is 0.08. And here I simulated the data with an amplitude of 0.08. So despite the non-stationarity, the stationary components of the signal look pretty good. Okay, so the final thing I wanted to say is that when you have EEG data or any neural time series data, when you look over a long period of time, there are always going to be non-stationarities. There are always going to be very strong transitions or noticeable transitions in the amplitude characteristics or the variance or frequency characteristics of the data. However, when you look at a relatively short period of time, so let's say a window of some hundreds of milliseconds, the data often exhibit characteristics of stationarity in short windows. So you can already see this by looking at this long time series is obviously very non-stationary. But if you would just focus in on this little piece of the time series here, it looks like there is some stationarity in this signal over here. This is another motivation for performing not frequency analyses, but time frequency analyses, where we perform the frequency analysis on short windows of time, successive short windows of time. and that helps to make the results of the frequency analysis, the Fourier transform, for example, more interpretable because stationarity is preserved within those small time series. So we hear much more about this in the next lectures on time frequency decomposition.